The following videotape is produced by the International Association of Fire Chiefs with a grant from First Alert. The goal of this program is to increase the effectiveness of first responders to residential carbon monoxide detector activations. Carbon monoxide is an odorless, colorless, non-irritating gas. It is this quality of being invisible that makes it difficult to find and elevates the threat of carbon monoxide poisoning.
When you walk up on a scene of fatality, and you look around and you say there's absolutely no reason why this person should be dead. There's no destruction, there's no trauma, so you feel that this can be preventable.
CO is a byproduct of combustion. Natural gas, propane, charcoal, oil and wood are just a few of the fossil fuels that produce carbon monoxide. When combustion is incomplete, more carbon monoxide is produced. Carbon monoxide poisoning is the leading cause of accidental poisoning death in America, according to the Journal of the American Medical Association. 1,500 people die annually due to carbon monoxide exposure. 10,000 more seek medical attention.
And then if we can teach people how to recognize the signs of carbon monoxide poisoning, if we can teach people that they need to have carbon monoxide detectors so that they can detect it in the earliest stages of exposure, we can prevent these unnecessary deaths and the significant exposures as well.
Symptoms of carbon monoxide poisoning often mimic the flu.
You would expect to see symptoms of headache or nausea or fatigue. Those are the most common symptoms. Oftentimes, however, those symptoms get confused with, well, you must have the flu, you must have the food poisoning, and so those symptoms are easily confused for other diseases.
At low levels, subjects may complain of headache, fatigue, nausea, and dizziness. At higher concentrations, carbon monoxide causes convulsions, unconsciousness, and death. It is important to understand that carbon monoxide does not affect everyone the same. Many populations are at greater risk. The elderly, young children, those with heart or lung disorders, and the unborn are more vulnerable to this highly toxic gas. When you breathe carbon monoxide, it enters the bloodstream, displacing oxygen that's needed for life. CO binds to hemoglobin in blood 240 times more aggressively than oxygen. Once in the system, carbon monoxide can take twice as long to leave the body as it does to accumulate.
The average half-life for a human is about 5 hours, which means that if you have 20% carboxyhemoglobin, 5 hours later, you're going to have 10%.
CO poisoning results from exposure to carbon monoxide gas measured in parts per million over a period of time. This corresponds to a blood gas level measured in carboxyhemoglobin, the compound formed when CO binds to hemoglobin in blood. For example, 100 parts per million over 90 minutes is equal to about 10% carboxyhemoglobin. Residential carbon monoxide detectors are designed to go into alarm before healthy adults feel any symptoms around this 10% point. Carbon monoxide is a pervasive problem in many homes. Since the energy crisis in the mid-70s, weatherization efforts have virtually sealed homes airtight, providing no way for carbon monoxide to exit the home. With less drafts come fewer air exchanges, providing less oxygen for combustion and upsetting the delicate balance essential for proper ventilation. Exhaust vents and clothes dryers contribute to a home's negative pressure. Downdrafting and reverse stacking are common sources of intermittent CO buildup caused by negative pressure conditions. Downdrafting can occur when outside air pressures become greater than inside, causing flue gases that would normally exit the house to reverse direction. With no draft established, the appliance spills its emissions into the home. Simply opening a door can correct the problem, making it difficult to determine the source of carbon monoxide. In poorly vented utility rooms and confined spaces, combustion appliances often compete for available oxygen. Reverse stacking occurs when one combustion appliance, like a furnace, pulls its oxygen down the exhaust flue of a nearby appliance, like a hot water heater. It only takes the slightest change in air pressure for a natural draft to reverse. This condition is common, but can be difficult to recreate. Operating a car in an attached garage, even with the garage door open, can draw CO into a home. It's not uncommon to measure high levels of carbon monoxide being pulled through the door jamb at the garage entrance. When a furnace is located in the garage, car exhaust is often pulled in and distributed through the home's ductwork. In November of 1994, a father and his two sons were killed in Los Angeles while the family car was being warmed in the garage with the garage door open. The mother and daughter were hospitalized in critical condition. Carbon monoxide filled the rooms where the family slept as the toxic gas was being circulated by the furnace located in the garage. In 1993, Kingston, New York became the first city in the U.S. to pass a law requiring carbon monoxide detectors. Today, other cities like Chicago have joined the trend, adopting similar legislation to require CO detectors in homes. Rick Salzman is the Assistant Fire Chief in Kingston, New York.
Public awareness of carbon monoxide poisoning is on the rise. Homeowners are purchasing carbon monoxide detectors as a first line of defense against an invisible killer, and carbon monoxide calls are increasing. As a department, this presents you with the challenge of receiving the proper training and equipment before handling CO calls. But it also allows the opportunity to provide a valuable public service. When the fire department is called to handle a CO alarm, homeowners rely on our experience to give them answers. Is my family in danger? What should I do when my alarm goes off? Will I have to call for furnace repair? Carbon monoxide is a pervasive problem, but it is often difficult to find the source. As responders, we need to be aware of the facts about carbon monoxide. Is carbon monoxide a genuine health and public safety issue? Absolutely. Is every CO alarm call a life-threatening emergency? No. There are many factors to be considered when learning how to respond properly and to be effective. Before you get into a situation unprepared, consider addressing these issues. Open a dialogue with your local gas company. Talk about what your roles are going to be. Will they follow up every investigation? When will they be available for assistance? What are your expectations from each other? Talk these things out before you run into problems. Establish a liaison so when questions come up, the appropriate parties can discuss them. There are a variety of CO detectors on the market today. At last count, there were 24 manufacturers listed with Underwriters Laboratories. UL tests consumer products and sets standards for product safety, reliability, and operation. UL Standard 2034 governs residential carbon monoxide detector performance and has been developed with advice from the medical community. The standard requires that detectors alarm as an early warning before hazardous conditions exist. To help identify the characteristics of these detectors, let's talk about how they work. There are basically two kinds of technologies being used by manufacturers. The most common detector uses a biomimetic technology that attracts and releases carbon monoxide in the same way the human body does. The biomimetic sensor uses a synthetic form of hemoglobin that attracts CO the same way as blood. The sensor darkens when exposed to carbon monoxide. An LED light measures these changes and triggers an alarm at preset levels determined by UL. As the sensor is exposed to clean air, it will recover. The manufacturer makes these charts available to check the CO sensor module. To check the module, remove it from this drawer located in the detector. After you've removed the module, find the colored dots that are located within these prongs. Compare these to the colors that are on the central module. The darker the color, the more exposure to carbon monoxide the detector has had. One more thing about this type of detector. Because it works like the human body, it has to have a half-life. It can take 2 to 48 hours for a sensor to completely recover. The sensor pack should last from 2 to 3 years, and it can be replaced. These detectors operate with a battery that is built into the sensor module. This type of biomimetic sensor is exclusive to First Alert. All other detectors use a common technology that incorporates a semiconductor sensor. This type of electronic sensor consists of a heated element that measures CO in the air, cycling on and off every few minutes. The sensor will lose electrical resistance if carbon monoxide levels increase and will activate the alarm when the CO level is too high. These detectors require AC current to heat up the sensor and must be plugged in or hardwired. While carbon monoxide is just slightly lighter than air and may initially rise when heated, it will eventually distribute evenly throughout the house. The plug-in type detector should not be installed on a switched outlet or in a location that can easily be knocked off the wall. Before responding to an alarm, it is important to separate non-emergency calls from those that might require more immediate action. We do this by interviewing the caller. Are they speaking clearly, or do they sound disoriented? Ask the caller if they feel any symptoms, headache, nausea, or dizziness. Confirm all members are awake and accounted for. Verify the alarm is a CO detector and not a smoke detector. The basic criteria used to determine whether a call is an emergency is the condition of the caller. If no symptoms are present, instruct the resident to ventilate and turn off combustion appliances. If symptoms are present, we advise that they evacuate the house and we respond with appropriate equipment. You stand a much better chance of finding the source of carbon monoxide if you follow a standard procedure for conducting a CO investigation. Heidi McGuire from the Kingston Fire Department will go through the recommended procedure for conducting a thorough carbon monoxide investigation.
We responded to this residence for a CO threat alarm. The first thing we're going to do is we're going to zero out our meter. And you're going to do this outside in the fresh air. After your meter has zeroed out, you're going to take an initial reading inside the front door. After you get your initial reading, follow your department's standard operating procedures on what level is acceptable for your parts per million. Your department will have a specific requirement for when you should need to put on your full turnout gear, including your self-contained breathing apparatus. Now we're going to go inside and check all the possible sources for this carbon monoxide. I noticed also that this house has an attached garage, so we'll take a look at that too. Our department operates off of a checklist when we have carbon monoxide calls. This enables us to make sure we don't miss any steps or sources for carbon monoxide. The first thing we want to do is we want to interview the occupant when we arrive at the scene. We want to make sure they're not suffering from any headaches, fatigue, dizziness, nausea, or any flu-like symptoms. If they are, we're then going to ask them, do they feel better when they leave the house? If they say yes, then we're going to be more concerned about a possibility of a CO threat in the house. We're also going to ask them how long their CO detector has been going off and what they have done since the CO detector has gone off. Did they open any windows to vent out the house? Did they turn off any appliances? After we enter the house, we want to close up the windows, we want to turn back on the appliances and try and recreate the worst possible situation that caused the CO detector to go off. Also using on our checklist is that we have a source checklist. This enables us to follow every single possible appliance or cause for carbon monoxide, including fireplaces, unvented space heaters, gas appliances, including ranges, dryers, hot water heaters, and furnaces. Also barbecue grills on porches near windows and attached garages where they're running their car. We see here that they had a fireplace going. We're going to check and do a visual inspection of the flue and make sure that the damper is open. We're going to make sure that there's nothing clogged up there. We're also then going to take a reading with our detector. We're going to turn on the thermostat and give it a chance to warm up. We're also going to turn on all the other appliances in the house. And now we're going to go around and check for other possible sources of carbon monoxide. We're now going around the house to look at all the possible sources for carbon monoxide. We notice that they have a barbecue grill on their screened-in porch. It hasn't been used in a while, but this would be another concern, especially because of the overhead roof enclosing the porch. You want to make sure when it's being operated that the sliding glass door is closed and the window from the kitchen is closed due to its close proximity. We're now in the kitchen to check another possible source for carbon monoxide, the oven and the stove. We're going to turn the appliance on and give it a chance to warm up. You also want to check and see what kind of venting they have above their stove. Does it vent to the outside, or is it a recirculating vent and it just pushes it back into the home? This stove happens to have a griddle on it. You want to be careful when checking for carbon monoxide because the cold surface, when it touches the hot flame, will burn at a lower temperature, therefore causing more carbon monoxide. We've now let the oven and the stove warm up for about 5-10 minutes while we turned on all the other appliances in the house. We're going to be checking for any excess carbon monoxide readings that might be coming off while the stove is burning. We're also going to check the oven. When we get done with this, we'll do a visual inspection of the pilot lights as well as the flame and make sure that they're burning cleanly. And that should be burning blue also. We're here the boiler now. The thermostat upstairs has been turned on, giving it a chance to warm up and burn off any CO. And we're going to open it up. We're going to check our pilot light and make sure it's burning a blue light. Visually look at it, make sure it's not white or yellow. If this was a hot forced air system, we'd be concerned about the heat exchange. We'd check that and make sure there's no cracks in it. The next thing we'll do is we'll check the flue. We'll visually inspect, make sure there's no separations in any of the elbows. Following all the way back, we'll check where it inserts into the chimney and make sure there's no separations. We'll also check with our meter. Remember that CO is tasteless and colorless, so you have to rely on your meters. And then we'll do a match test. We're checking the draft. And it's drafting up. Now we'll check the hot water heater. We'll take the access plate off. And we're going to get down and do the same thing. We're going to check and make sure that our pilot light is burning blue. This has been running for a while, so it's up to temperature. We'll also do a check with our meter. Remember, we're looking for CO. CO is odorless and tasteless, so we have to rely a lot on our meters. Then we'll come around and we're going to check our flue. We're going to do a visual inspection as well as an inspection with our meter. Any rust or corrosion, we're going to make sure there's no holes. We'll look back. We'll follow all the way back to where it meets the chimney area. Here we have a possibility of reverse stacking taking place because of the fact that the flue from the hot water heater is connected to the flue of our boiler. Be very careful that if both appliances, if they're running at the same time, that the hot water heater isn't actually getting dirty air from the boiler, which can create some CO problems. And then we'll do the match test. And that was fine. The gas dryer has now been operating for a few minutes. The first thing you want to do is pull the access panel off. That'll enable you to take a look at the pilot light. Next thing we want to do is take a reading with our meter. We're checking for any excess CO. Then we move to the flue piping. You want to visually inspect it, make sure there's no cracks or separations of the piping from the unit, and then take a reading with your meter. Remember, if you happen to have flexible flue piping, to make sure it's not kinked. We're now at the door, which is the entrance to the garage from the house. Even when the garage door is open with the car running, the exhaust fumes can still come in through the door jamb. We want to measure here to see if any CO is leaking in through the gaps.
If you're going to verify a CO alarm, you'll need to use the proper metering equipment to measure for carbon monoxide. Here are some purchasing considerations your department can use when evaluating equipment needs. The single biggest consideration when purchasing equipment may be your department budget. So consider the capabilities of the unit you're going to buy. Single gas meters are less expensive, ranging from about $200 to $800. They typically read carbon monoxide in parts per million with a digital readout. Multi-gas meters are more expensive, but can be used for a variety of other applications in addition to just CO, such as confined space rescue and hazmat. Therefore, they can be ideal for a variety of situations, but may cost between $1,200 and $2,500. Consider the sensitivity of the unit. You'll want a meter that can read a range as low as 1 part per million up to lethal levels, several hundred parts per million. Also consider ease of operation and choose a meter that has a proven track record for fire department use. Don't forget about storage and handling needs. Will your meter be shock and moisture resistant? Think about the day-to-day use. You'll also want a meter that's third-party tested for safety and reliability, and one that has good technical support. Understand that the procedures outlined in this program are recommendations that have proven successful in the field. We hope your department will use this information as an outline to help establish your own protocol.
The primary objectives when conducting a carbon monoxide investigation are to recreate the conditions at the time of the alarm, put the residence in its worst condition to help identify the source of carbon monoxide, also interview the occupant to determine what the situation was like at the time of the alarm. To help recreate the potential for downdrafting, turn on all possible exhaust devices before starting combustion appliances. This includes range hoods, bathroom vents, gas or electric clothes dryers, and attic fans. To check for cracks in the heat exchanger of a forced air furnace, measure for carbon monoxide at the register vents. Because most of the heat exchanger is not visible, it's difficult to visually check for cracks. If carbon monoxide is leaking through a hole in the heat exchanger, CO will be circulating through the ductwork and may not be measurable at the furnace. When investigating for carbon monoxide, remember that appliances like ovens, ranges, and space heaters may be more likely to contribute as a source of CO because emissions are not vented to the outside.